Good evening, ladies and gentlemen. I am here again to talk to you about my project, the relationship between raccoon presence and proximity to water in the Arcata Community Forest. And also I'll be sharing some results on the proximity to urbanization, which I found to be interesting. So I'm going to go over the background, the methods, the results, as well as the application of these results, and the conclusion. Why should we care about raccoons? A brief background. Raccoons are associated with water. It's listed as a critical habitat feature. It's required in their habitat. But that doesn't necessarily say that they spend most of their time by water, or that you will detect them more by water. So that's what this study is designed to do, is address where in the landscape you are most likely to detect raccoons. And the study area I chose is the Arcata Community Forest because it supports a population of raccoons. The methods I used were deploying track plates with one track plate at a site with water, and then each site was paired with another site that did not have water. That was at least 33 meters away from that site, the site with water. So there's sites with water and sites without water, and their presence or absence was recorded. That's a binomial response. It's either 1 or 0 for the categorical presence or absence of water. Track plates were baited with cat food and bacon fat, conveniently providing breakfast, because you're just using the fat as the bait, not the bacon itself. And the track plates were checked the next day, and yeah, the presence was recorded as either a 1 or a 0. So the results, I got 8 detections out of my 32 track plates. Sites with water had higher detection of raccoons, and there's a p-value as a result of the Fisher's exact test. And the interesting result that I found during the course of this study that I wasn't really intending to go for, but I did find, was that sites closer to urbanization had a higher detection of raccoons, and it's statistically significant. So if we look at the chi-squared analysis here, and this is referring to all of the sites, so sample size is 32, we see that for our chi-squared analysis we get a p-value of 0.001, and the test statistic exceeds the critical, so this is a significant result that across all of the sites, the presence of water was a successful determinant of raccoon detection. And this result was even more clear when you divide the sites into close to urbanization and far from urbanization. The sites close to urbanization had a 100% success rate in the classification of presence or absence based on presence of water, with a p-value of 0.0001, whereas the sites far from water had about a 55% correct classification rate, which means it's really no better than random in deciding whether, in determining the probability of use, with a p-value of 0.3, so the test statistic for that does not exceed the critical value. So that's the model did not work far away from urbanization, but it worked quite well close to urbanization. Perfectly, actually. 100% successful classification. The problem with this is that with a chi-squared analysis, you're not allowed to have any more than 20% of your expected values to be less than 0.5. And as we can see here, all of them are less than 0.5. So unfortunately we can't use chi-squared analysis. We have to use Fisher's exact test, where you calculate the p-value by hand. And that's easier said than done. But after you finally get it right and remember how to do factorials, you come up with some good results here. We have a p-value for all the sites of 0.001. So across all the sites in the entire forest that I sampled, all 32 of them, the presence of water was a good predictor of the presence of raccoons, and it was correct 75% of the time. And within the sites close to urbanization, same as before, 100% correct classification with a really good p-value of 0.0002. So when you narrow the area that you're focusing on to sites within about 600 meters of urbanization, you get a really good predictor. And the way I came up with the cutoff threshold for what is close and what is far is by creating a resource probability selection function. This takes the binomial response of raccoon presence or absence and maps it against the meters to urbanization. So this plot has a bunch of points down here for presence, or down here is for the absence of raccoons at sites, and then their distance to urbanization, and then up here we have some points for sites that had raccoons at them and the meters to urbanization. And the majority of points with presences were down here, the majority of points with absences were over here. So with logistic regression, we fit this curve to these points, and this is the output that we get. And with a cutoff threshold of 0.5, take it down to the line, you see we get about 360 is our cutoff threshold. But that's kind of not appropriate because the highest that we get to is 0.8. So if you cut that in half, you get 0.4. Take that over to the threshold, you take it down, you get about 550. And the correct classification, due to our model of water at sites less than 600 meters, was very good, and above it is not so good, because no matter whether there's water or not, you're not going to get a detection if you're above 600 meters, or the probability of it is about 20% probability. So that's and you can measure how good this model is by looking at this ROC curve over here. If this was totally random, then the line would be right in the middle where this gray line is here. That would have 0.5. 50% of the area would be underneath that line, and that would indicate that it's not a good model. And anything above 0.6 is considered a good model, and this is 0.8, so this is a really good model for the data that we have. And here's a quick little demonstration of how to use this resource selection probability function. First we'll look at this red dot here. We'll say we're trying to determine the probability of a raccoon occurring at this site. So all you have to do is measure the distance from this site to urbanization, which I calculated here as 1,300 meters. Put that on our x-axis here. Take it up to the line and over, and that will give us the probability of use, which is 0.1. So you're approximately 10% chance of that site being used just based on its distance. And similar for this site down here at 200 meters, you get a 0.65 probability, so 65% chance that you're going to encounter a raccoon at that particular site. Why do we care about raccoons and water and resource selection functions? Well, raccoons they can be a pest, they can get into your garbage, they can be a problem, and they're ecologically important because they're predators of endangered animals, they're prey for a lot of animals, and to understand the sites that you are likely to encounter them it's very, very useful. And in relation to water, they mostly transmit disease. They're raccoon roundworms near water where their latrine sites are. And in terms of resource selection probability functions, it's a non-invasive tool that can be used to model site use. So you can use a single variable that you get off of looking at a map to determine the probability of raccoon presence. So it's a really powerful tool when you combine all of those, and you can use it for a lot of cool things. Thank you very much, and if you have any questions, please let me know.